For almost a century, APA has been the technical leader for our entire industry, bringing objective, thorough, unbiased, and uncompromising research, innovation, standards, and credibility to our members and their customers. APA's brand and reputation stands for unrivaled integrity throughout the marketplace, and we are proud of what we stand for and what we deliver to our membership each and every day.
Hello everyone, and welcome to our webinar. Our topic today is titled Designing Engineered Wood Diaphragm Systems for Panelized Roofs. My name is Bob Cusick, and I will serve as moderator for the session. Our speaker today, Alita Dean, and I both work for APA, the Engineered Wood Association. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, APA conducts research to improve engineered wood construction systems and educates users and specifiers on the product's proper use and potential applications. Before we start today's webinar, I need to cover some housekeeping details. Alita's presentation will last about 50 minutes. Handouts of the slides can be found in the chat on your screen. To ensure that everyone can hear the webinar clearly, we have muted all participants. While we are bookending the discussions with our cameras on, we will be turning them off during the session to maximize the connectivity of the webinar. During Alita's presentation, we encourage you to submit questions by typing them into the questions page in the control panel on your screen. We will answer some questions in the chat box, and we will answer some questions in the Q&A at the end of the session as time permits. The recording of today's program will be posted on our website, www.apawood.org, in a few days. I'd also like to note that today's webinar is approved for AIA and ICC continuing education credits. About an hour after the conclusion of the webinar, an email will be sent to each attendee. It will include a link where you can get customized AIA and ICC certificates of completion. Your feedback is important to us. I would like to point out that you see a QR code on your screen. If you open your camera on your smartphone, a link will pop up to take you to a survey on this session. The link will be also emailed to you in about an hour after the conclusion. Let me introduce our presenter today, is Alita Dean, Engineered Wood Specialist for APA based in Los Angeles. In that role, Alita works with designers, building officials, and builders to provide construction and design direction for the use of APA member company engineered wood products. Prior to joining APA, Alita worked as a structural engineer for 9 years in the San Francisco Bay Area and Los Angeles. She's a licensed professional engineer in the state of California and an active member of SEOC. And for those of you just joining us, welcome to Designing Engineered Wood Diaphragm Systems for Panelized Roofs. Again, I will mention to maximize the size of the presentation on your screen, and Alita and I will turn off our cameras, and I will now turn control over to our speaker, Alita Dean.
Thanks, Bob, and thank you everybody for joining us today. I'm going to get us started in just a moment. Thank you. This is a brief description of today's webinar. Lateral load paths include many building elements, but today we're going to be focusing on the diaphragm. If you're interested in learning a bit more about load paths in wood construction, APA has several on-demand webinars related to this topic, and you can find those at apawood.org. Our goal today is to give you a basic understanding of the diaphragm design process for large diaphragms with the IBC. We're going to start with some basics before launching into some examples. So the examples should help you understand how to specify your sheathing and nailing based on your loading. We'll discuss sub-diaphragm design, and we'll finally look at how our choices are affecting the overall diaphragm deflection. So starting with the zoomed out, really high level view, our goal in any building is to provide a complete load path to the foundation. So the load path is the route the forces are taking, passing through the structure. This route is going to be made up of building components and connections as the force or load makes its way into the ground. The vertical load path is referring to the load path that gravity force takes. That's acting on the weight of your building as well as anything inside your building, and that vertical load path is how we funnel all of that gravity force into the ground. The lateral load path consists of wind loads and seismic loads. One of the things people find surprising a lot of times about lateral loads is that in some cases these loads are actually going to move upward through the building and through the roof and floor diaphragms that carry loads to the walls before they move back down. But just like the vertical loads, all lateral loads must have a continuous path that ultimately takes them down into the foundation and out of the building into the ground. So again, today we're going to focus on diaphragms, which are part of the lateral load path. Path for any force is going to start at the location it's applied on the structure and then end at the ground. So we're starting with a really easy lateral load path example here. The forces here are beginning at the wall. This is step 1, seen here, and then they're transferring into this roof diaphragm through step 2. So that's where you're looking at this orange arrow here. The connections labeled here as step 3 are transferring the loads between the walls and the roof. The roof diaphragm then transfers the force to the walls at each end of the structure through the connections. So those are the walls at either end of the structure, and we're labeling that as number 4 here. The end walls then transfer the load into the foundation, that's down here at number 5, and through the foundation those loads are getting into the ground. So that's how we're completing our load path. This is a really basic load path through a single-story building. Now, because seismic loads are based on mass, the highest loads usually get applied at the floor and roof levels. Wind loads are based on surface area, so it's going to depend on the geometry of your exterior. Both the wind and the seismic load paths are going to rely on that roof diaphragm to distribute the loads over to these end walls out here on the sides. The first step in lateral force design starts with determining the loads that need to be resisted. Chapter 16 of the IBC governs the structural design of buildings and structures that are regulated by code. And Section 1609 in the IBC specifically details the wind load requirements be in accordance with chapters 16 to 20 in ASCE 7. And then you have Section 1613, which details earthquake loads be in accordance with chapters 11 through 15, chapter 17, and chapter 18 of ASCE 7. I've omitted this step for our example today. There are several resources already available that detail this load determination, and we're going to be focusing just on the diaphragm design today. I would like to point out, though, that the next edition of ASCE 7 that's already out has an alternate method for calculating forces for rigid wall flexible diaphragm structures like the ones we're looking at today. Chapter 23 of the IBC provides minimum requirements for the design of buildings and structures that use wood and wood-based products. The NDS, which is the darker green book shown here, is used to design all the basic wood components and connections. IBC section 2305 requires structures using wood frame shear walls or wood frame diaphragms to resist wind, seismic, or other lateral loads be designed and constructed in accordance with ANSI AWC's special design provisions for wind and seismic. I'm going to call this SPIDWIZ from here on out. Special design provisions for wind and seismic is quite a mouthful, but this book is available for free, view-only download on American Wood Council's webpage. I've stuck the URL here. AWC also has a number of pre-recorded educational webinars, including a 2021 SPIDWIZ update. If you haven't checked out these courses, take a look. They're at awc.org. So getting a little bit into the meat, wood diaphragms are typically comprised of wood framing and sheathing. The shear values are a function of panel grade and thickness and fastener size and spacing. That ANSI AWC SBIDWIS has tables 4.2a, b, and c, and those are providing the nominal unit shear capacities for wood frame diaphragms. And that's going to be for blocked wood structural panel diaphragms, blocked wood structural panel diaphragms with multiple rows of fasteners, that's our high load diaphragms, and unblocked wood structural panel diaphragms, respectively. We're going to be referencing table 4.2a multiple times today. So again, 4.2a is blocked wood structural panel diaphragms. Currently, diaphragm tables in the IBC only contain values for stapled diaphragms. The SBIDWIS lists the nominal values for diaphragms using common nail fasteners. The tables were reformatted in the 2021 edition, and you'll see what that looks like a bit later when we get into the example. But all of the tables in this webinar are referring to the 2021 SBIDWIS. These tables are divided based on 6 load cases, panels installed with their long axis either perpendicular, so that's these up here, or parallel down on the bottom row. Keep in mind the panels should be installed perpendicular to the support to achieve the rated span for the sheathing. This is noted in footnote A here. Panels that get installed parallel to the supports may have a lower span rating, and that should be considered for your vertical loads. Panelized roofs like the one we're talking about today, those are typically framed with the panels parallel to the supports. So the span rating that's written on the panel stamp, it won't apply if you're supporting those panels parallel to the long axis or parallel to the strength axis. So today we're going to be looking at a simply supported diaphragm with no interior shear walls. Now the load on a wall, any given wall, is actually resisted by the walls that are perpendicular to it. So we get longer load walls like this one generate more load than a shorter load wall. Longer resistance walls generate more resistance than shorter resistance walls. Most buildings are rectangular, not square. So that means that a lot of times we're trying to resist larger loads from those long walls with a shorter resistance line. So we're trying to fit all our resistance into a shorter resistance line. Wood diaphragms are limited to a 4:1 aspect ratio. This is in SBIDWIS. This kind of provides a natural limit to the amount of tributary diaphragm load per foot of diaphragm depth. Loading and resistance occurs in both directions. So here you can see the shorter load wall is being resisted by the longer resistance wall lines. I find it helpful to think of a diaphragm like a beam, so similar to how a gravity beam transfers the vertical load to its supporting studs. The diaphragm's job is to transfer the lateral load to the resistance wall lines. To get the load from the perpendicular wall to the resistance wall lines, we're going to rely on that diaphragm in bending. As with any beam, the bending capacity is heavily reliant on the material at the top and bottom of a beam. So if you think about like a steel beam, we call this material the flange, that extra material that we have at the top and the bottom. On a truss or a diaphragm, we're going to call that material the cord. So here we're showing an exaggerated deflected shape of the diaphragm with the cords at the top and bottom. Unlike a simple span gravity beam, our diaphragm will get pushed in multiple directions. So our chords will need both tension and compression capacity. Because unlike a beam, we don't have one single tension side of the beam and one single compression side of the beam. So our chords need both tension and compression capacity to handle the lateral load coming from either side of the building. The example that we're going to walk through today can be found in APA's L350 publication titled Diaphragms and Shear Walls, Design and Construction Guide, along with some additional examples of shear wall design. So if you haven't seen this before, take a look. It recently got updated. We're going to walk through 5 basic steps that every diaphragm design should include. You'll notice here that our lateral loads are already labeled. So again, we're not going to go over how to calculate these loads today. We're starting with these loads already assumed. As I mentioned earlier, wood diaphragms are limited to a 4:1 aspect ratio. So this is a clip from the 2021 SPIDWIZ with our diaphragm aspect ratio limits. You'll notice from this table that the limit gets reduced further if we decide to omit blocking or if we're using a layer of lumber instead of wood structural panels for our sheathing. And this is because the way those assemblies perform under lateral loads is different. So we've got an aspect ratio of 1.6 to 1 for our example here. So we know we're easily meeting that 4:1 aspect ratio limit. Next step, we need to calculate the diaphragm shear, see what kind of loads we're looking at. Now again, I've omitted the derivation of those loads using ASCE 7. Assuming our 516 pounds per lineal foot lateral load in the north-south direction, we're going to multiply that by the length of the load, 192 feet, divide it by 2 with half of the load going to each end wall, and divide that by 120 feet to get our pounds per foot along the edge of the diaphragm in that short direction. Just to show you what an interior shear wall would do to that load, if we split this diaphragm span in half, the diaphragm shear gets split in half, and this is because we reduced that 192 feet to 96 feet. If you stick an interior shear wall in exactly in the middle of this diaphragm, this interior shear wall is going to have twice the amount of load compared to the exterior end walls. And that's because it's receiving half of the load from diaphragm A and half of the load from diaphragm B. So back to our simple diaphragm that we're looking at today, we're going to look at the shear load in the east-west direction. So this load is slightly larger at 525 pounds per lineal foot, but the diaphragm is shorter. So we come in at well below that 413 pounds per lineal foot, and that 413 pounds per lineal foot is going to govern our design. Next, we need to take the diaphragm shear and design our sheathing and nailing. So this is where SPIDWIZ table 4.2a comes in. I'm sorry if it looks a little bit blurry on your screen. The new 2021 SPIDWIZ only shows the nominal shear values, and it's using factors to differentiate between wind or seismic, as well as between ASD or LRFD. Instead of before, we had separate areas of the table. So this shift didn't affect most of the ASD values, but if you're using LRFD for your design, your capacities have now dropped 12 to 13% across the entire table. If you're working in ASD like we are today, you can also use Table 3 in that APA L350 document that this example came out of. This table is using the 2.8 factor for seismic ASD design on those SPID-WIS values. So this table has values for both blocked and unblocked diaphragms, but it's assuming seismic ASD as a base. If you look at footnote B on this table, it has a provision for increasing this value by 40% if you're doing a wind load design. So if this 413 pounds per foot is an ASD level wind load, we're looking for a minimum of 826 pounds per lineal foot in the SPID-WIS table. I've highlighted all of the options that meet that criteria in yellow. You'll see I went straight into table 4.2a for blocked diaphragms. Again, if you've got an unblocked diaphragm, you need to go to table 4.2c. But also remember that for the unblocked diaphragm, you also have a different aspect ratio limit. Both the tables will have similar formats, but the values are gonna be different. You might notice at the top of the table we've got these cases listed in parentheses. It's up here, both levels. These are the 6 cases to find the nominal unit shear for a diaphragm. And as a reminder, before we use any of the cases shown on the bottom row, I'm going to reiterate that panels need to be installed perpendicular to supports to achieve the span rating specified on the panel stamp. If you install the sheathing with the strength axis parallel to supports, you'll need to do some extra calculations for your vertical load and vertical deflection. Our diaphragm is using case 1 in the east-west direction and case 3 in the north-south direction. The thinnest panel we can get away with for lateral load is a 3/8 performance category struck 1 panel. This is a bit thin for our vertical loads and may not be available depending on where your project is located. Instead, we're going to opt for the 15/32 performance category, rated sheathing. So struck 1 is up in this upper area, and the rated sheathing is down in the lower portion of the table. We're opting for this 15/32 panel down here. Going with the rated sheathing instead of the struck 1 panel is going to get us a more flexible panel, so we're not going to do as well on the panel stiffness, but again, the struck 1 may not be available in your area, so it really pays to know what your contractor can get. Now, if that 413 PLF is an ASD level seismic load, we're searching this table for a minimum 1,156 pounds per lineal foot. So this forces us to tighten up our nailing. If we stick with the same 15/32 performance category panel, we're going to need a 2.5 inch on center boundary nailing. For seismic, it's probably easier to just go use that L350 table to find any options higher than 413 PLF. This just has the factor already applied for seismic ASD. You might notice we can reduce our boundary nailing if we opt for a larger nail. I've stuck with the 15/32 panel because that's the most common roof sheathing I see in my area, but if you can get a thinner performance category to work for your vertical loads, more power to you, go for it. As it is here, we're looking at 2.5 inch on center nailing at the diaphragm boundaries and 4 inch on center at the other panel edges. In practice, that nailing will look like this, with 2.5 inch on center nailing at the boundary out here and along the continuous edges, and then 4 inches on center at all these other panel edges. For larger roofs, you might consider reducing that nailing based on the diaphragm shear demand. So just like a beam, our shear is a simply supported beam. Our shear is higher at the ends of the beam, but reduces down to 0 at the center of the diaphragm. So you don't actually need the higher nailing at the center of the diaphragm. You can divide the roof up into zones. This is very common with larger roof diaphragms. So here we've split the diaphragm into 3 different zones, and this approach can help you reduce the amount of labor and the cost efficiency for your building. Zone A is at the ends of our diaphragm, so it's going to get that 2.5 inch nail spacing that we just calculated for the highest shear area of our diaphragm. But zone B, it drops down, so we've got 344 pounds per foot here. And you can see here we can loosen that nailing up a little bit to 4 inches on center. Zone C drops down even more, so this is the bulk of our roof area at the center. 275 pounds per foot is our required diaphragm shear. For zone C, we could potentially loosen up that nailing even further to 6 inches. You'll see our 275 pounds per lineal foot is slightly over our allowable 270 pounds per lineal foot. This is about 2% over, so depending on your own engineering judgment, you might call that good and call it a day, or you could potentially up your framing member size to 3x at those adjoining panel edges and boundaries. Zone C covers the bulk of the roof area, so this should make your contractor much happier if you can reduce the nailing in that area. The actual panel specification should look something like this. So we've got a 15/32 performance category panel, exposure 1, rated sheathing with a 32/16 span rating. The span rating is determined by your vertical load. So the 32/16 happens to be the predominant span rating for this performance category. This is a handy table in APA's Form D510. This is a panel specification guide, and that shows you which span ratings can be produced in each performance category. The bold text here is going to show you the most common performance category for each span rating. You might notice that there isn't any bold text in the 1/2 inch or the 3/4 category. These are less common performance categories, so don't be surprised if you end up with a 15/32 or a 23/32 in the field once the contractor actually goes and tries to source the panels. Next up, we're going to look at chord forces. So remember, our chords are giving our diaphragm that bending capacity. So we're using our simple span beam bending equation, that WL²/8, and we're dividing that by the distance between our chords. With this simple diaphragm, the distance is also the depth of the diaphragm. So you can see right off the bat, our north-south direction is way higher. So the chords along grids 1 and 2 need to resist quite a bit of tension and compression. If we start assuming a 2x12 ledger for our chord, let's look at our tension capacity. We're going to turn to the NDS to get this equation. We're using Doug for a large number 1 species. So we've got a base value of 675 pounds per square inch. We're going to adjust for short duration loads. So that's because we're looking at a wind load. And that's where we get this 1.6 factor here. And I've assumed the ledger is preservative treated with some incising. All of this gets us to the 14,586 pounds, which isn't quite enough for our demand. So we're going to need to bump it up to a 3x12, which we're going to want anyways at areas of heavy nailing. It gives us a little bit more room. And that'll get us to 24,304 pounds easily. Wood does really well in compression parallel to grain, so our compression capacity in that 3x12 is easily going to meet the load requirement. And you can see that just by looking at this pounds per square inch number. The other job our diaphragm is performing is anchoring the walls in the out of plane direction. So with concrete or masonry walls, this seismic load can get quite large. In these cases, we sometimes use a sub-diaphragm to help stiffen specific areas of the diaphragm and funnel that load into a few chosen diaphragm cross ties. And this allows us to reduce the number of hardware we use in our diaphragm ties, running the full 192 feet of the diaphragm. Wall lines where the roof framing attaches at convenient intervals, like at grid lines 1 and 2, we have a lot of potential anchorage points at fairly large framing members that can serve as our cross ties. These cross ties can also only have a few breaks, requiring hardware across the girders. We're going to design a sub-diaphragm for the walls along grid lines A and B. So by funneling that out of plane anchorage load into the girders, we can take advantage of the more robust framing that's already continuous the full length of the diaphragm in the east-west direction. The process is iterative, so we're going to choose a sub-diaphragm depth, go through these steps, and then adjust as we go if needed. Now, unlike the rest of the diaphragm, our sub-diaphragm is going to have a tighter nailing and therefore higher stiffness to handle this anchorage load. We're going to start with 16 feet. Typically, in these types of buildings, our purlins are laid out at 8 feet on center. So we're going to try to stick with multiples of 8. With our framing plan, we've got girders framing into these walls at 40 feet on center. So to calculate the sub-diaphragm shear, we're going to take that 750 pounds per foot, per lineal foot, and multiply it by half of the span between the girders. And then we're going to divide that by the sub-diaphragm depth that we're assuming. So that's a 16 feet. This gets us an ASD level load of 938 pounds per foot. So we're looking at 2,625 pounds per foot in our SPIDWIZ table, because this is a seismic load. Unfortunately, the largest capacity in that table 4.2a is 2,295 pounds per foot. So we're going to need to extend that subdiaphragm a little further if we don't want to go to multiple rows of fasteners. If we redo that shear calculation with a 24-foot depth, we can get this down to a more reasonable range. So you might notice we're moving things around in increments of 8 feet. Again, that's typically the spacing of the purlins in a building like this. This is also very typical of a panelized roof, but your project might be a little bit different. So try to stick with whatever spacing your project is working with. If you recall the capacities we determined earlier for the different zones, you'll see the 1750 subdiaphragm demand is exceeding even our zone A capacity. There are a couple options to fix this. So we can increase our nailing at zone A. We can also size up our nailing and go to a 10 penny nail, or we can increase the subdiaphragm depth. These are a couple different options. You choose what's right for your project. Here we're going to increase the subdiaphragm depth and we'll move it to 32 feet. We don't need to change the sheathing if we do this or the nailing at zone A. Checking our cord capacity, we've got a much smaller demand. That's the 4,688 pounds required for our cords. The 3x2 ledger we picked before is going to be more than enough, but you'll also need to check the capacity of the purlin at 32 feet. These aren't fully braced in the weak axis, so you may need to beef that line up or add bracing to make this line out here at the interior edge of your subdiaphragm to make sure that is working as your subdiaphragm cord. With that subdiaphragm obliterating the zone B we had, we're now down to 2 zones. So we've stuck with that 15-30 second category sheathing, but now we have a zone A and we have a zone C, and we got rid of our zone B nailing. The anchors themselves are designed based on tributary load. So for your purlin anchorage, you're looking at that 8-foot purlin spacing that we're assuming, and you're multiplying that by your out-of-plane wall load. So that's at 750 pounds per lineal foot. So each of those anchors, those purlin anchors, needs to be resisting 6,000 pounds. And our sub-purlins are at 2 feet on center spacing. So we're going to be looking at sub-purlin anchorage forces, at least through our subdiaphragm, that meet this 1,500 pound force. Our girders, on the other hand, they're spaced at 40 feet on center, and again, that's where we're funneling all of our out-of-plane load, and you'll see these have a much higher 30,000 pounds, but that's because we've only got 2 of them running the entire length of the diaphragm. Turning to our diaphragm deflection, this is table 4.2.3, straight out of SpidWiz. Since this is a simple diaphragm, we're looking for the worst case deflection directly at the midspan, so it's at that 96 feet. I'm going to point out that SpidWiz uses a 3-term equation, and that breaks out the deflection due to bending, shear, and cord slip. Now, based on our design, we can calculate each of these 3 terms by plugging in the relevant information. Note the shear equation doesn't take into account our multiple nailing patterns. So right now it's assuming that we've got a zone A nailing everywhere with OSB sheathing. The shear term is about 77% of the total deflection here. So if we look at the 4-term IBC deflection equation, we can parse out where that larger portion of the deflection is actually coming from. The IBC equation separates the shear deflection term into panel shear and nail slip deflection terms. Now, because we have multiple nailing patterns, for this 4-term equation, we're going to adjust this 0.188 coefficient to account for those multiple nailing patterns. APA recommends adjusting this term based on the shear load per nail over the length of the diaphragm. This diagram charts the load per nail, assuming zone A nailing over the whole diaphragm, so that's this area 1 on the left. And the diagram on the right shows the load per nail with our zone A and C nailing patterns. So just by comparing these areas, that's how we're going to adjust that 0.188 coefficient. So going back just to remind ourselves, our load per foot at zone A was 413 pounds per foot. And that's how we came up with that 2.5 inch on center nailing at the boundary. Area 1 is equal to the load per nail at zone A multiplied by half of the diaphragm span and then divided by 2. So that's that load per nail we're getting with 413 pounds per lineal foot. And then we're multiplying that by 2.5 over 12 to get the load per nail. So we land at 97.7 pounds per nail in zone A, and multiplying that by the area, we get 4,690. From our shear diagram earlier, we know that the diaphragm shear at 32 feet is 275 pounds per foot. So to get our load per nail for area 2, we're dividing this by the number of nails per foot. Then we have all the pieces to calculate the area of this trapezoid out here at area 2. Area 3 is straight up a triangle, so it's a bit more straightforward. We're taking that same 275 pounds per foot and we're dividing it by 2 nails per foot in zone C. Multiplying that by the triangle base divided by 2 gets us our area 3. So if we input those into this equation, we've got a revised nail slip coefficient of 0.276. So that's a really hefty increase because, again, that zone C covers a lot of our diaphragm area. So the center of our diaphragm is much more flexible because we dropped the nailing down in that area to 6 inches on center. To our 4-term equation, we'll pull our G sub T value from APA Form D510. So that's this panel design specification. If you've never seen this document before, I highly recommend you download this. It has almost every mechanical property for your wood structural panel, separated out by performance category and even span rating. Now, due to the higher nailing at the high demand areas of our diaphragm, our worst case load per nail actually occurs at zone C, where we calculate 137.5 pounds per nail. That worst case is what I'm going to input here, and this is going to get us an E sub n of 0.13. As kind of a side note, this is over 2 times the E sub n we would get if we use the 97-pound shear at zone A. The load per nail is going to make a big impact on your slip value. So if you find yourself with drift issues, you might consider tightening up your nailing as your first option. It's going to have a lot of impact. If we input those two numbers, we'll get the deflection based on our sheathing design, 0.24 inches, and the deflection from our nail slip, which is 2.12 inches. So this really highlights what we're saying about the nail load impact on your diaphragm flexibility. I put the SPIDWIZ breakdown in here just to compare, so you can see that ignoring the change in nailing is going to mean your deflection estimate is really unconservative. In both cases, though, your nailing choices are contributing the most to your overall deflection.
Thank you, Alita. Before we begin our Q&A, I'd like to remind you that your feedback on today's webinar is important. It counts. The QR code shown on the screen will link you to today's survey. Just open your camera on your smartphone and a link will take you to the survey. Alternatively, a link will also be emailed to you in about an hour. Please take a minute and fill that out. So we did get a few questions, Lita. We're running short on time, so we'll see if we can get a few in before our hour runs out. The first question we got was, how come you only did a sub-diaphragm in one direction?
Okay. Yeah, the sub-diaphragm is really going to help reduce the amount of hardware, and that decrease in hardware is related to the continuous cross tie requirement. So the largest benefit is really going to be in the longest diaphragm direction with the most number of breaks in the perpendicular framing. So for our example, those are both true in the east-west direction, but in the north-south direction, we've only got 2 breaks in the framing continuity, so it's not going to save as much hardware. So that's why we only did it in the east-west direction.
Okay, thank you. Next question we got is, do I need to use overstrength for the anchor design?
So I'm thinking this is for our sub-diaphragm example where we talked about anchors and wall anchorage. The overstrength is part of the requirement in chapter 12 of ASCE, and it's for the steel elements. So the steel elements of your wall anchorage, they do need the overstrength factor. So if you've got, say, like an embedded strap in the concrete wall that's tying to the wall to like a wood joist, the steel strap should get a 1.4 factor for all of the steel-related failure modes, but not the wood connection or concrete failure modes. That's for the steel failure modes and not the wood failure modes.
Okay, very good. Next one, why are you using a different sub-diaphragm load than the first example?
Oh, okay. Well, the first example is really our overall building lateral loads. The sub-diaphragm loads are for our out-of-plane wall load rather than the overall lateral load. So that's the out-of-plane wall anchorage. Depending on the height of the wall, the footprint of the building, these can be really different loads on the diaphragm. So they're unlikely to really be the same.
Okay. On slide 30, I don't know if you recall slide 30, but I think you show that a 3/8 inch panel would work. Why are you using a 15/32 inch panel?
Yeah. The thinner sheathing might be accurate for or adequate for the horizontal forces, but the thinner panels also need to resist the gravity forces. So you start to get into kind of serviceability concerns, which really effectively means your roof is going to feel bouncy, or you may even overload it with your live loads. Because this type of panelized roof typically runs with the strength axis of the panels parallel to the supports, you're going to see a significant capacity drop off from the perpendicular condition. And I know we have a tech note on that topic, just looking at the vertical load difference between panels laid perpendicular to framing versus parallel to framing. I think it's Form Q 225. But you can see in the tech note that it's very different. So we went with a thicker panel because that thicker panel is going to be closer to meeting your requirements for the vertical load. So yeah, we could have said for this example, hey, use that thinner panel, but you're probably going to change it later on anyways because of your vertical load.
Okay, yeah, thank you, Lydia. That tech note Q225, that is a useful tech note. And remind people that we do have lots of tech notes available on our webpage that'll help you out of just a lot of conditions with APA. Another question is, what should I do if the sub-diaphragm shear is higher than the SPIDWIZ tables?
Oh, okay. So if you're over the 820 pounds per foot allowable shear, you could go to maybe multiple rows of nails. So there's, again, that high load diaphragm table in SPIDWIZ. But if your demand is still too high, or if maybe you just want to stick with the single row of fasteners, you could increase the depth of your subdiaphragm, like we did earlier. But that's higher nailing over a larger portion of your roof.
Okay, Alita, I think we're out of time. That's probably about all the time we have for questions today, because I got a few housekeeping things we'd like to take care of at the end of the seminar. The first thing I'd like to mention to everybody, so make sure you're signed up and receive our APA update newsletter. This will help. It'll get you notified of our next webinars and future webinars and updates to any APA publications and standards. To receive it, all you need to do, starting with the home page on our website, is to click in the sign in on the upper right-hand corner of the page, and a menu that will drop down to simply select register. From there, you'll need to let us know what you'd specifically like to receive, which in this case is the APA update newsletter. Additionally, I'd like to mention that APA has resources to assist you at our help desk that can be reached through our APA email at help@apawood.org, or you can call and phone in at 253-620-7400. Finally, I'd like to point out, shown on the map here, that APA has field staff located throughout the country. Your local APA engineered wood specialist located in the region shown on the map is also a free resource that is available to you for this type of assistance with diaphragms and many other engineered APA questions you have regarding engineered wood products or construction. Their individual contact information can be found on the staff contacts page of the APA website. At this point, I'd like to thank you all for attending and thank you for joining our webinar.